Well, good afternoon. I would like first to thank the organizer, especially Rama, and wish a happy birthday to Srini. And without further ado, I'll proceed to my talk. So this work was done in collaboration with Pablo Minini in University of Buenos Aires and one of his students, Patricio Di Leoni, who's now doing a postdoc in Rome with Luca. And well, during the year, we've published a number of things. So I'm going to basically just concentrate on the last two. However, I will have to go quickly. First of all, about generalities about Gross-Pitaeveski Equation, because like in Ladik's talk of this morning here, in this talk, h bar is not equal to 0. So there are some particularities. And then I need very quickly to remind you two results about Kelvin waves and helicity. And then I'll go to my to the main topic of my talk, which is actually the behavior of helical quantum turbulence, and in particular, finite temperature effects. Okay, so this is the Gross-Pitaeveski equation. So this looks horribly quantum. It looks like a Schrödinger equation, but thanks to the Madelung transform here, we can translate this equation into hydrodynamic variables. And it turns out that you have quantized vortices. So here is Madelung transform. You get this is the speed of sound. You have a coherence length, which is special to the quantum flows. So first, you have the conservation equation. This is completely equivalent to this equation. And then you have this, which looks exactly like a Bernoulli equation, except you have a term that has more derivatives than the other. And this term is responsible for the dispersive effects and is related to the coherence length. Okay, so here there is some cheating because I'm saying that V is the gradient of phi, and phi is not defined on the nodal lines, which are just the superfluid vortices. Okay, I need a technical point, which is that using Madelung's transform, we can define fluid mechanical kinetic energy, and also internal energy, and a quantum energy that correspond to the quantum pressure term. All these things were defined in this old paper. And let me just emphasize that in this old paper, what we showed is that a Gross-Pitaeveski analog of the Taylor-Green vortex was deploying Kolmogorov turbulence. And so basically what I'm going to talk about today will be a helical case, which is Taylor-Green vortex is non-helical. Okay, so first technical point I need, the Kelvin waves. So the point I'm going to make is that Kelvin waves are very important in quantum turbulence. And there is a way to measure them in numerical simulation, and that is to perform spatiotemporal spectra. So you've seen all that. This is Gross-Pitaeveski, Madelung, the equation in Madelung's terms. And here is why I cheated, which is that here I write V equals gradient of phi, but phi is not defined on the lines. And in fact, this is a true equation. The rotational of the velocity, omega, is a distribution with the delta. It's like, the vorticity is like the current in a thin wire, if you want, okay? And this explains that you have the quantized circulation around the vortices, okay? So, okay, I'm going in the wrong way. Okay, so first of all, Kelvin waves have this dispersion relation, and this is the dispersion relation of sound waves with the dispersive correction. This relation is called Pogolyubov, okay? And this is due to Lord Kelvin himself. And this is a simulation of the Taylor-Green vortex, and in the little thing here, I have extracted one vortex, and you can sort of see that it's got wiggles on it. And the question is, people will see that and say it might be Kelvin waves. I remind you, Kelvin waves are helical waves propagating on the vortex lines, okay? So the resolution of this is to perform spatiotemporal spectrum. So this is K omega. The way you do that is you output regular fields when your simulation goes on, and then you take a Fourier transform in time, and then you recover the spectrum K omega. And so here we can see the dispersion relation. This is the one for sound waves, and here is the Kelvin wave thing. And so you can find that there is indeed some excitation on the Kelvin wave thing. So now you can play an interesting game, which is you can fill this spectrum of omega k. By construction, if you integrate on omega, you recuperate the spectrum E of k, the usual one-time one. You see the color map. So yellow is a strong and red is not strong, weak. And this line is the dispersion relation for Kelvin waves. So you see some excitation along the line, okay? So now what you can do is you can filter, you can put a filter here and keep only the data along the line, and then redo the one-time spectrum, and you get this. So now you get the energy spectrum of the Kelvin waves. And interestingly, it's got something that is closer to -5/3 than to -7/5. I'm not pretending that this is but it goes in that direction. So this was just to make, you couldn't, of course, extract that part if you are dealing only with the vertical integral, which is the one-time spectrum. You need a spatiotemporal spectrum to be able to do that. That was the basic point. So now I go to my second technical point, helicity. What? I have 24 minutes already? Left. Aha. It's a countdown. All right. I was okay. So I go to my to my second technical point, so which was covered in this paper. And now the question is, okay, we want to have helicity is something. Well, let me go to the point. Helicity in a classical fluid, earlier on Navier-Stokes, is this quantity, which is quadratic. It's the velocity times the vorticity, which is the rotation of the velocity. And this is a quadratic invariant of Euler equation that was discovered more than, I don't know how many centuries after the Euler equation by Keith Moffat and other peoples. And it has very interesting topological properties. Actually, you can see that this thing is conserved. Let me just say what I mean by topological is whatever vector is advected by whatever velocity. So let's take advected as a vector, like a magnetic field in MHD. Magnetic helicity will also be conserved. So my point is you don't need, this is the advector, this is the vorticity. This is conserved because the vorticity obeys the same equation as the magnetic field, but any field that obeys the same equation as the magnetic field will have a conserved helicity. So there is, I can't do that with them. Well, I'll come back to that later. There is a nice topological argument. Okay, so what about quantum flows? So I said the vorticity is this distribution, okay? How is the velocity in a quantum flow? Well, if you look at the velocity, it's got a singularity on the line. So actually there is a r-1 singularity on the line. So if you think of it, your vorticity has a delta singularity on the line, in the direction of the line, and the velocity has a 1/r singularity perpendicular to the line. So when you were little in school, they told you, you should never multiply two singular distributions, right? So this you cannot define. But there is a good sign is the two singularities are perpendicular. So maybe we can make some sense out of it, okay? And well, so I don't have time to go into that because anyway, it's only a technical detail. Those who are interested can go back to the paper. But let me just say that, so formally, here you have a good distribution. And here you have a velocity that has a perpendicular singularity. So, okay. You know the velocity is the gradient of the phase. On a normal point, standard point, the constant phase surfaces are stacked like that and the velocity is perpendicular. When you have a vortex line, the constant phase surface, they all intersect on the vortex line like that. So when you do the gradient of the phase, you get this 1/r singularity. So if you want to define the velocity along the line as a gradient of phi, you get 0/0. But then you can use L'Hopital rule, and the idea is the velocity along the line, regular one, will be the rate of twist of the constant phase surfaces. Okay, that's all I say. So doing this, you do get this complicated thing. Now, this thing has an interest, which is that, okay, it's complicated, but look, it's a regular expression of derivatives of the psi field. So this means that if I program this in a code, okay, I can get a value of helicity from the 3D field. just compute it, do a loop, compute, and I get this. So, okay. This is also, people doing topology, they have these things. The right, which is something really, I don't have time to go into the details, the twist and the link, and there is a relation with the SEM. Let me just say that with the definition we took, they give the good numbers for simple vortices. So let me just show you what happens in a simple case of reconnecting knots. So this is a trefoil knot, and this is two linked rings. And you can actually follow the helicity, and in some cases the helicity is not conserved, and in other cases is conserved. I will not go into the details. I will just... this is Gross-Pitaeveski equation, of course. Why is it not starting again? Yeah, this is solutions of Gross-Pitaeveski equation. We didn't invent it, but we implemented it. There is a technique. You can set up any knot you want inside Gross-Pitaeveski and then integrate it forward in time. Okay, so this several people do that. I mean, it's a little bit involved, but not too complicated. So you see a reconnection of a trefoil knot here. You can actually follow the helicity. Sorry. So let me just say a good thing about Gross-Pitaeveski. People who use Biot-Savart methods or things like that, it does not contain reconnection. So you have to put ad hoc rules about reconnections. Here, the equation itself is non-singular. I mean, it's a nonlinear wave equation, and the vortex is just a nodal line. So it just does the job without any problem, without being singular. The singularities are only in the Madelung transformation. They are not in the evolution equation. Okay. So now I am on to my main topic. So I will talk about dual cascade in helical quantum turbulence. So I wrote in a slide before that in this old 97 paper with Noor, etc., we basically defined the energy spectrum. There was another technical thing in this paper, is to define a way of getting nice initial data to do vortex dynamics. Let me explain why you need that in just a word. A Gross-Pitaeveski equation admits sound waves. It's a compressible flow. You know that if you start a compressible computation with any initial data you put in, you will in general generate a lot of sound waves that will miss your computation. If you want to do a low Mach number flow, that is a flow with, that's what you are interested in, not shock waves going all around the thing, but a low Mach number flow, you need, in a compressible code, to have some algorithm to have an agreement between your initial velocity and your initial vorticity. So let me just stress that many people in the field don't do that, and so their Gross-Pitaeveski equations are often spoiled by too many sound waves going around. So anyway, so I go into the technical thing. I'll just go through the red things. This is the so-called ABC velocity flow fluid, which is for classical fluid flow, is a standard thing used by numericists to study highly helical flow. It is made of three parts, A, B, and C, which are just obtained by circular perturbation of X, Y, Z. And one of them, let's say A, for instance, it's a velocity that is constant in a plane pointing in a direction. And when you go perpendicular to the velocity, it turns around, okay? So it's a maximally helical flow. And it's actually an exact solution of earlier equation if you put a single wave number. This is the ABC flow. So the question here is, how do we get inside Gross-Pitaeveski equation something similar to the ABC flow? Well, there is a technical trick which goes into two things. I don't have time to get into it. And when you do this, you get some initial data. Then you have to message the data in such a way that it will not do like a firecracker and all kind of sound waves. So we did very high resolution simulations. So this is the initial data. Remember when we had the helicity? You had a gamma square here. This is a quantum of helicity, okay? It's the square of the circulation. So this flow here has 45,000 quanta of helicity. Now, I just stop 1 second to comment. I said that we get the same thing with our formula that works in the whole cube. We get the same thing as people doing it with knots, measuring array and twist, etc. So the way they do it normally is first, they extract the vortex line, then they apply algorithms to the vortex line in order to get the link, the rise, and the twist, and then they get the helicity, okay? So what we do here, imagine that you'd have to do this. Each one of these little things is a vortex line. It would clearly be a nightmare, okay? But here you use our formula and you just compute the helicity. So again, this is the initial data. So what we do... I don't know, your guess, I haven't counted them. I can measure the total length, it's somewhere in the paper. So, you know, the measure of the vortex length is actually the length per unit volume. So it's actually 1 over a square length, and it's actually 1 over the square of the mean distance between two vortices. So between two vortices, you have a mean distance, which is very important. I think Ladik talked about that. And so 1 over L square is the length of spaghetti in one cubic meter of... okay. So this is in the paper. I don't know the number like that. So now we take that as initial data and apply GPE. This is what you get. So first, the helicity. Second, the energy. Incompressible and compressible energy. So how is it? And this is the vortex line. This is the incompressible energy. This is the helicity, and this is the total vortex length. Okay? So apart from the, so you have two GPE computation, one which is at 2048, one which is at 1024, and you have just, not for quantitative, but for qualitative purposes, you have a Navier-Stokes computation of the same classical flow, okay? So of course you don't have the vortex line in the Navier-Stokes, because there is no vortex line in Navier-Stokes, but you can see that the decay of the helicity, the fact that first the helicity is stable, because remember Euler conserves the helicity, Gross-Pitaeveski doesn't conserve helicity. This is high resolution, high Reynolds number Navier-Stokes and Gross-Pitaeveski. So we first start emulating Euler and we conserve helicity, but then finally helicity decays, okay? Meanwhile, this thing is the total length of vortex is growing, it will finally decay. And the energy, well, when you get in the Kolmogorov regime, it's decaying, okay? So if you look now at the, I remind you a very nice and old papers, 1973, which has been verified many times, I guess, in the Navier-Stokes framework. So when you have a dual helicity and energy cascade, which is our case here in the decay computation, then you get the usual Kolmogorov thing for E of k, but you have this prediction for the helicity spectrum. Eta is the helicity injection rate. Epsilon is the energy injection rate. So the prediction is -5/3. And in our case here, where it's a decay, we don't really have injection, we have a decay. We can measure epsilon and eta just by looking back to this curve. So the derivative in time of this, actually minus the derivative in time of h, is eta, and minus the derivative in time of EKI is epsilon. So from the previous thing, I can plot my spectrum and plot these things, and I have no free parameter. Now, this is what you get. So I'm not saying it's absolutely fantastic, but you do get, so of course, the initial state by construction, remember we made a Gross-Pitaeveski thing that would look as much as possible to the classical ABC flow. Remember also that classical ABC flow is an exact solution of Euler equation. So we did not start with a single ABC flow. We started with one ABC at K0 equal 1 and plus one ABC at K0 equal 2, so that we have an initial dynamics that works. So you can see by the initial data energy spectrum that our procedure worked in the sense that most of the energy is in the first two modes, okay? But then when time goes on, the energy is spread around and you get this -5/3. Now the helicity spectrum here also has a zone in -5/3. Of course, you have to look at times in a reasonable interval, not the initial data, but the peak of dissipation. This is the compensated helicity spectra. So you see it's quite good, the agreement, okay? All right, and now if we compute Kelvin waves on these flows, we see that the final flow, I mean, that is at the time of the peak of dissipation, there is a huge amount of Kelvin waves excited, okay? So, and if we do visualizations, this is a visualization of a part of the cube here. This is the full computation. You have this thing which, so this is all made with the quantum vortices, but they make a tornado-like structure. And let me have a quick thing about the basic topological thing. So this is the thing I usually do with my glasses, but I won't be able to do it, so I'll mimic it. If you take two strings and you put them around your finger, you have helicity in the form of right, which comes from the thing like that. If now you put it, it's a straight line, but the two are twisted together. So it went from right to twist. And now it turns out that in a classical vortex, it's like this. And this thing, so you see, that's what I said, right can be transformed into twist. Okay, so now if you look at the structures we have, so I take a shot here, I blow it up, I got this, I blow it up again, I got this. So if you look at them, you see that because of the Kelvin waves, you have things like this happening. So when you have something like that with a bunch of vortex line, then this classical helicity conservation method, going from right to twist, works. But when you have a single one, has the vortex line itself has no internal structure and no twist of internal lines, then this will dissipate helicity. So I insist, this helicity is weird, it's not conserved. The only thing conserved by Gross-Pitaeveski equation are total number of particles, I mean total mass, momentum, and energy. There is no conservation of helicity. So we believe that this is the mechanism by which helicity is destroyed at small scales. Let me just comment that this is interesting because it's been like 15 years that people had the same idea about energy. Energy is cascading down to the length between two vortices, is cascading in basically a classical way because the bunch of vortices work like classical vorticity. And then when vortex reconnect, energy is transferred into Kelvin waves. And then in order to dissipate it, you need to study the cascade of Kelvin waves in a wave turbulence sense. Well, what we are saying here is that the same thing should be done for helicity. There is clearly the same mechanism for helicity. Okay. Now, one last thing before I go to the finite temperature thing. The last thing is that remember that we had all these structures here. So if you think of a structure like that, it means that, let's say here I have nothing, so the vortex lines are non-polarized. Here I have a classical tornado, and the vortex line will be more or less all in the same directions. So we try to quantify that, because trying to look at this thing is a nightmare. And to quantify it, we did this. So the idea is to do a correlation function of the density, okay? Spatial correlation function of the density. Now, remember that the vortex, the density is 0 on the vortex. So if you have a bunch of aligned vortex line, you will have two directions in which the vorticity the density will vary very quickly, and a third direction in which the direction of the vortex bunch, in which the density will not vary much. So what we did to quantify that was to compute the correlation matrix of density, okay, and measure its ratio of eigenvalues. And the thing is consequent in the sense that if, wrong button, what, wrong button. This is for this field that you have here, and we compute the correlation function, and we do averages in the region where we have structures, and averages in the region where we don't see any structures, okay? And when we compare the ratio of eigenvalues, it's completely different in the region when there are structures and the region where they are not. So this seems to confirm, which you can see by the eye looking at the visualization, which is that Gross-Pitaeveski does a good job of reproducing classical structures such as vortex filaments, etc., as bunch of vortex line. And the trace of that is that there is a polarization of the vortex bundle there. Whereas in other regions like that, you see, I mean, you can have regions where you have a clear polarization and regions where you don't. And this ratio of eigenvalue helps you quantify it. All right. So now I go. So the experiments are performed in general in a situation where you are not at zero temperature. And there is one way to include temperature in the Gross-Pitaeveski equation, and the idea is that to Fourier truncate it. So it's well known in the Bose-Einstein condensate community, following papers by Davis et al., that truncated Gross-Pitaeveski equation goes into an absolute equilibrium, exactly like truncated Euler goes into an absolute equilibrium, okay? And the absolute equilibrium of Gross-Pitaeveski actually contains a phase transition, which is the equivalent of the Landau transition. That is, if you are below a certain energy, you get a condensation in the lowest lying mode. And if you are above the critical energy, you lose it, okay? So a lot of people have used that. However, it's rather difficult to generate the fields in this way because it takes a long time to converge. And also, when you do it this way, what you control is the energy and not the temperature. So what we advocated was to actually make a grand canonical ensemble. And I don't have time to go into these details. Again, it's in the paper. You have a stochastic differential equation that goes into this probability. Now, if you look at that probability, by the way, and if you remember that the energy E has a quartic term, and if you are not too young and you remember the 70s, you realize that this is the Hamiltonian for second-order phase transition for a complex order parameter. So it's not, no wonder that truncated Gross-Pitaeveski equation has the right phase transition, okay? Because this is just a Hamiltonian with a lambda 5,4 with a complex parameter. So anyway, the result, because I want to show the result and not the theory, which is detailed in the papers, is you integrate this stochastic differential equation. This is a white noise. You integrate it in time. So you see it's a diffusion equation. There is no I here. And there is a Lagrange multiplier, another Lagrange multiplier that we will take to 0 in these studies, and white noise. And you can check that if you integrate that, it's been done several years ago by Giorgio Krustulovic and myself. You can check that the ensemble you generate like that are completely similar to the one you generate by running truncated Gross-Pitaeveski for a very, very, very long time so that it equilibrates. So our method to do the finite temperature initial data is, remember when we were doing ABC at 0 temperature, we had some psi. Now here I have another psi, which is the finite temperature thing, and I just multiply them, which adds the velocity. So that's the procedure. So let me first show you the initial data. So this is just to show that the code works and reproduce. This is the ratio of T over T lambda, and this is the density of the K equals 0 mode. So you have the standard condensation transition. This is the mass spectra of the initial flow at different temperatures. And, okay, this is the initial data. So you already saw it at T equals 0. I was saying, look at the incompressible kinetic energy. It's very nice. I've reproduced only the 2 modes I want, and all the other are 0. So when I increase the temperature, this is more or less fine. But on the other hand, if you look at the compressible energy, the sound waves are in it. They are not in the incompressible. And you see that increasing the temperature puts a bath of sound waves. So this classical model is you have the vortex, and you put finite temperature as a bath of sound waves at equilibrium. And then you integrate that forward in time. So let me show you the results. First of all, if you look at the flow, especially when the temperature is high enough, you do see the structures you had before, but the vortex are all messed up. It's really impossible to see them, at least in the density, but they are there. And second, look at the time evolution of energy and helicity. So they are the same things, but on the left, they are lean, and on the right, they are lean log. So exponential behavior is a straight line on the right. And so T equals 0 is what we had before, is the blue. And the other one are increasing the temperature. So you see that initially, when I increase the temperature, I have normalized my energy to have the same energy. And you see that if the temperature is small enough, there is no big effect. But when I increase the temperature, I obtain a decay and I completely lose this Kolmogorov phase. Here, same for helicity. Now, the highest temperature, the one that are of the above lambda, but like 0.6 T lambda, I'm almost finished. Like 0.6 T lambda, you have an exponential decay. Okay, this is to confirm the decay. What you look at here is the logarithmic derivative of the energy, and here is the logarithmic derivative of the helicity. So you see that when you go to very high temperature, it's flat. Okay, and this is a different spectrum: kinetic energy, helicity, compressible kinetic energy, showing what is happening. Now, it's better to show the compensated spectrum. So this is the dynamics of the compensated energy spectrum. So T equals 0 is the one on the top, okay? So it's K minus 5/3 compensated. So you can see that when you reach the maximum of energy dissipation, it's reasonably flat here. You can see that this is still good for the lowest temperature, but it's completely spoiled in the highest temperature that are decaying like hell, okay? Now, same thing for the helicity spectrum. Okay, so you have the same behavior again. Highest temperature is decaying exponentially, and the lowest temperature, they behave like T equals 0. Okay, so summary. So our results show that this model, I didn't have time to go into that, but there are many, many ways to try to put finite T effect in Gross-Pitaeveski. Okay, this is only one of them. You have many other models. So, but we try this one. So this model seems to work in the sense that we do get some kind of a viscous classic flow for the highest temperature with exponential decay. And that this pseudo-viscous effect, I mean, basically putting finite temperature, everything decays faster. And we have some quantification of it. Now, when the temperature... This is the helicity spectrum. So in this case, you have so many vortex that you can just average. So you see, that's energy, sorry, this is helicity. So it's noisy here, and when it's negative, it goes away, but in the large scales, you have so many vortices that the noise is completely swamped out, okay? So, I mean, you can see it here. It puts some strong dissipation. Now, I must, okay, I've said all that. I must confess that I was somewhat disappointed by the result in the sense that I don't know how to control dissipation. They are just there. So I would have liked, well, if you think of it in some way, the viscosity will be controlled by the mean free path of the waves, okay? Because it's a path of thermalized waves. So I don't know, I'm thinking of how to control this mean free path, but it has some finite value at temperature, and my feeling now is that you would need a much, much higher resolution to, you see, it's a little bit like, the box is too strong, so the mean free path of the waves is too large with respect to the box. Okay, so that's it. Happy birthday again.
We can have a few questions.
You said lots of interesting things. Could you give me some 2 or 3 important things I must remember?
Okay, so there is one new thing, is that, okay, it was known that you can reproduce the turbulent cascade you have in Navier-Stokes, you can reproduce with Gross-Pitaeveski. Now we know you can also reproduce the Helicity cascade, Gross-Pitaeveski. This was not known before. Second thing, all these computations are at T equals 0, and we are trying the best we can because we want to say something, hopefully, about the measurement they are making in Shrek in Grenoble. You know this experiment. Yeah. So they are running basically with a half of normal fluid and half of superfluid, okay? And we wanted to try to do something about that by adding the normal fluid as a gas of particles. The result is that it seems to be too viscous at the resolution we can reach. Or our computation box is too small, I don't know how to put it. So I'm kind of, maybe this means that this special model of finite temperature effect is not good for this regime, for this middle temperature regime. That's the short term.
Yeah, okay.
Any more questions? Okay, in that case, we'll thank the speaker and